Building the spanning tree. The first job of STP is to elect the root bridge. The root bridge is discovered as the bridge in the network or VLAN with the smallest identifier, priority combined with MAC address. So the root bridge, whether it's a VLAN network or a physical LAN, requires to have the smallest identifier, priority combined with MAC address. When a bridge initializes, it assumes itself to be the root bridge and sends configuration BPDUs with a root ID field matching its own bridge ID. But if it detects a bridge with a smaller ID, it ceases sending its own frames and instead adopts the frame it received containing the smaller ID to be the basis for further BPDUs it sends. The port where the BPDU with smaller root ID was received is then marked as the root port. i.e. the port on the path to the root bridge. The remaining ports are placed in either block or forwarding states. So what does that mean? So we will make it clear as we go. So let's start small. Every bridge starts blind. When you power on your network, every bridge, switch, or Linux bridge assumes I am the root bridge. It sends BPDUs out all ports with root ID equal my bridge ID. So this is how the root bridge send its own my bridge ID to the down frame or non-root bridge. Root path cost equals to 0. Bridge ID equals to my bridge ID. So as you can see, the root ID and bridge ID is the same because he is the root. These BPDUs are sent to multicast. It was sent by Linux or the OS, whatever OS it has. So initially everyone shouts, I am the root. Step 2, the best lowest bridge ID wins. When a bridge receives a BPDU from someone else, it compares receive BPDU, root ID, path cost, bridge ID, port ID versus my current best BPDU. So when a bridge receives a BPDU from someone else initially, it compares to its current best BPDU. So it is coded in its OS of that switch the currently best BPDU. If the received BPDU claims a smaller root ID, lower priority, or lower MAC, the receiver realizes, wait, that bridge has a better claim to be root than me. So step 3, marking the root port. At this point, the bridge does this. First, it adopts the root ID in the received BPDU, so it now believes that smaller ID bridge is the true root. And then it adds its link cost to the root path cost in the BPDU. And then it marks the port that received the BPDU as its root port. So this is how marking happens. It adopts first the root ID that has the smaller ID bridge compared to its currently best or smaller ID or the currently highest priority, and then it add its link cost before it mark that port to be the root port that will be used to connect to a designated port. The root port is equals to the port on this bridge that gives me the lowest cost path to the root bridge. So this is all about the cost. So the reason why you receive that to that port is because the root is closer or closest to that port. Another thing is this root port, alternate port, could be another bridge, which we will later see. Or usually it's another bridge. It's rare that the alternate route is not within the port of your bridge, because other bridge from could have uh, lower path costs than the other ports on your bridge. So that's the logic. We will see that visually later. There can be only one root port per bridge. So that's another characteristic. Bridge B receives BPDU from A. Root ID equal A. Cost equal 0. So these are the properties received from the BPDU from A to B. B adds its link cost, say 4. New cost equals to 4. B marks that port as root port. So that's what happens. Conceptually, step 4. Marking designated ports, the forwarding ones. Now bridge B still has other ports, may be connected to bridge C, D, etc. What should it do with them? B send out new BPDUs from those other ports with root ID equals to A, the true cost. So remember, the non-root bridge will only send frame downstream. So this is what it does conceptually. B sends out new BPDUs from those other ports with root ID equals to A, the true root. It basically telling the C that now the root is A. Root cost is equals to 4 because the path from B to A is 4, the cost to reach root. Bridge ID equals to B. Me, the sender. So you send those 3. So at first, as you can see, we only send root ID equals to A and then cost equals to 0 to B. But when we go to C, we now send 3 things. Its own bridge ID, the actual root ID, the root path cost. That's the reason why earlier we mentioned that we have a 2 bridge ID, because we're talking about a non-bridge route. So each segment link between 2 bridges elects one designated port, the one closest to the root. On that link, the bridge with the lowest total cost to the root becomes the designated bridge, and its port on that segment is the designated port. It forwards traffic for that LAN. So we will be clear, this will be clear later. So it basically means that whoever closest to the root bridge will become a designated bridge. Kinda like it is its root will be the one connected to the root or root bridge port root bridge designated port, because remember, root bridge doesn't have a root port, it only have designated ports, and its port on that segment is so that's what we mean by and its port on that segment is the designated port. It forwards traffic for that LAN. The other bridge port on the same link is either root port if it leads toward the root, or alternate or black port if it's redundant loop path. So what happened here, since we're talking about switch B, since it has the root port, so that's what we call the root port connected to the designated port of root bridge. But how about the other ports in switch B, for example? How can we know that it is a designated port? We can know if it's a designated port if it's the next port nearest to the root port or nearest to the root bridge. Okay, so why is that? How do we compute that? We compute that using the cost. So, and the other will be the backup port, and the alternate port again is from another bridge, which we will get clarity later. And those alternate port will get black because that will be the alternate port if the root link or root port failed. So step 5, the root bridge itself. For the true bridge, it has no root port. It is the root. Therefore, all of its active ports are designated ports, like what I've said. That means every port on the root bridge is in the forwarding state. One per attached LAN or VLAN. So all of that port is in the forwarding state. They are not blocked because they're allowed to always send, especially the frame every 2 seconds. That's why all of these ports in forwarding state, like the frame structure we discussed in the previous video. So if the root bridge has 1000 ports, yes, all 1000 can be designated ports, each on its own LAN segment. Step 6, blocking redundant ports. Every non-root bridge keep its root port forwarding toward root. So the state of that root port is always forwarding so that it can always receive packets every 2 seconds from the root bridge. It keeps designated ports forwarding downstream. So instead of forwarding upstream, which is what the root does, it is forwarding downstream to communicate downstream bridge. Put all other ports, those that would create loops, into blocking state. So this is how, or this is the magic of how STP make the avoid loops. These block ports still listen to BPDUs but don't forward user traffic until needed. So these block ports, such as alternate ports, still listen to BPDU, but their OS on that bridge or switch they are connected to, or the OS they are connected to, basically drop the frame and doesn't forward the packet that is being sent or forwarded from root port to root bridge and from designated port downstream. Step 7, summary table of port roles. Role root port found on every non-root bridge. Function, it's a best path to the root bridge. Designated port on each LAN segment, its best path from root to that segment. So a designated port is a best path from root to that segment. Remember, everything is going towards root bridge. So a designated port basically always connected to a root downstream, such as from root bridge to downstream bridge such as switch B, and switch B designated port to a root port downstream such as switch C or so D or E. Backup port, backup to a designated port on same bridge or segment. So this alternate port backup to root. So usually it is from another bridge. So this is the link that will take, later we will see a diagram for this, that will take by the the this entire network process that will it will be programmed for that link to activate in case this root port failed, because it is the next nearest to the root bridge. So we're just concerned about the cost of going to the root bridge. Backup port. Backup to a designated port on same bridge or segment. It is normally blocked. So this, instead of from another bridge, since it is not concerned about how near it is, I mean still concerned, but this is is not the nearest, the next nearest from the root port. So it is in the same switch or in the same bridge as the root port, recently failed root port. Disabled port, manually disabled, not participating. So you can disable this as an administrator. Putting it together with your code, let's reinterpret your text in the context. When a bridge initializes, it assumes itself to be the root bridge. It starts by sending BPDUs with its own bridge ID as root ID. If it detects a bridge with a smaller ID, it receives a BPDU with a better root ID. It ceases sending its own frames and instead adopts the frame it received. So again, it starts by sending BPDUs with its own bridge ID as root ID. If it detects a bridge with a smaller ID, if it receives a BPDU with a better root ID, it ceases sending its own frames and instead adopt the frame it received. So it uses an if else. If, for example, A now don't have the better root ID, it will adopt what's the currently best uh, root ID or highest priority. It stop claiming rootship and adopt the better BPDU's root ID and cost. So it will adopt the cost and will mark that as a new root ID. The port where the BPDU with smaller root ID was received is then marked as the root port. So that's how it marked the root. That's how it marks root port. The remaining ports are placed in either block or forwarding states. So the other port are programmed to be disabled if it's manually disabled, block if it's alternate or alternate route, and forwarding states if it's a designated or a root port. STP runs the port role election on each link, designated or blocked. So the STP will run port role election on each link for designated or block. Remember, the block still listening from that currently root, and it will stop and will do process re-election if it doesn't receive after 20 seconds. So you said when creating a link bridge like C or D that has the lowest total cost from B's bridge to the C and D's D route will become the designated port. That's exactly right. With one small refinement. Each linked LAN segment between two bridges has exactly one designated port. That's the port on the bridge that's closest to the root bridge, lowest root path cost. So for example, here, A, B, C. Suppose A is the root bridge. Path cost is A to B is equals to 4, B to C equals to 4. Now, A's root path cost equals to 0, B's root path cost equals to 4, C's root path cost equals to 8. On link A to B, A cost equals to 0, B's cost equal to 4. Therefore, A wins. So A port is designated port. And B's port is root port. So that's what happened because A's becomes the root bridge. So its port become the designated port connected to the B's root port. So this root port connect toward A. On link B to C, B's cost is equals to 4. And then C's cost is equals to A. The B wins, so B's port is designated port. And C's port is root port. So therefore, from C's perspective, the B is the root. From C's perspective, the B is the designated port that is provided to connect to the root port toward A to eventually reach the actual root, which is A. So yes, the bridge with the lower cost to root has the designated port on that link. So for example, you have B to C link. Whoever port is the closest to the root port of that C root port, C root port, which is usually the root port, which is the root port that has the lowest cost towards A, will become the designated port of that switch A. So what happens to the losing ports? Every other port that doesn't win or segment or isn't the root port will enter a blocking state. But here there are two different kinds of block roles. Alternate port, backup path to the root. Let me discuss this further. Okay, just a moment. Just a moment, guys. Yeah. So, what this mean is basically a root port is a relative, and it depends on the perspective of where you are in the topology. So, for example, in this ABC, in the perspective of B, its port connected to a designated port is the root port. But in the perspective of link from B to C, the port connected to that root A is now not a root port, but rather a designated port connected to the root port of C, meaning those port or those link are the path cost nearest to the root bridge. So that's what we mean by that. So I just want to clarify that. So yes, the bridge with the lower cost to root has this designated port on that link. So a bridge with the lower cost to root has the designated port on that link. So what happens to the losing part? So an alternate port exists when a bridge has two or more possible paths to the root bridge and one of them is better. For example, C and D. Here, both C and D have links to the root through B. E has two ways to reach the root, via C or via D. E will choose one path as its root port, say via C, lower cost. So here is the best explanation of alternate route. So E will choose either C or D. Now, if this C fails, so initially this C is the higher priority or the lowest cost, but if its C fails, it will turn into D. So that's the reason why the alternate port is from another bridge. So E has two ways, both C and D have links to the root through B. E has two ways to reach the root, via C or via D. E will choose one path as its root, say via C, lower cost. The other port to D is an alternate port. It's a backup path to the root in case the primary fails. Alternate ports listen to BPDUs but don't forward data. Block. So if the active root port fails, an alternate port can quickly transition to forwarding. So if it fails, usually it will send a signal to other connected path that will then later activate the alternate port. Kind of like TCP and TCB, TC frame or part of the frame will do in our network, like what we will discuss later. Backup port, backup to a designated port on the same segment and same bridge. So this one is rare. A backup port exists when two ports on the same bridge are connected to the same LAN segment. So for example, we have two port that is connected to the same LAN segment towards A. So that's how we get backup port in the same bridge, because we can technically fail into it in case the root port connected to the, say, root bridge designated port fail. So for example here, bridge B, how same harp or VLAN segment, both ports are physically on the same broadcast domain. Only one port can be designated for that segment. So one port is designated port forwards user traffic. Another thing is that for non-bridge, only one designated port could be at a time, because there's only one port connected to the root port of that LAN segment. For example here, so you can also imagine here from A to B, and B to C. So the one connecting to B to C only have one designated port connected to C root port. So here one port is designated port forward user traffic. So the designated port is the one forward user traffic. The other is a backup port. It's currently blocked because it's not needed. It's only there to fail into it, just like an alternate port. Backup ports are backed up to a designated port on the same bridge and same segment. So it's the same segment as well, not just the same bridge, because the one of the characteristic of an alternate port is they must be in the same on the same segment. While alternate ports are backed up to the root via another bridge. So blocking state summary. Port role, block traffic, no. Purpose, best path toward root. Can transition, yes, always forwarding. Port role, designated port. Block traffic, no. Purpose, best path from root to the LAN. So it is the best path for this segment from root to the LAN. So that's what it means, because there can only be one designated port on each bridge connected to the root port where you are currently sending it from, such as C, from C to B to A. So alternate port, block traffic, yes. Backup to root, yes, if primary fails. Usually you fail into it. And this is the main, and the backup port is rarer. Backup port blocks traffic, yes. Backup to designated port on same bridge or segment, yes, if designated fails. So another thing is that you configure this via Linux by specifically identifying ETH, or the actual port interface, and it doesn't need to be physically connected. Usually it's bind via virtual LAN. Disabled port, block traffic, yes, manually or administratively down, because like what I've said earlier, we can administratively disable a port. Now here's the simplified visualization. From root bridge A, connected to designated port, connected to non-root bridge, connected to root port toward A. Sorry, root bridge A has designated port that is connected to non-root bridge B with root port toward A. Now this root port toward A is the designated port toward C. As you can see, one port has two designation, can be root or the designated port, depending on where you look at it, whether it's toward A or toward C. Non-root bridge C, and it has a root port as well, which is connected to the designated port of B. If there's a loop like CD, BA in a ring, then the redundant port becomes alternate or backup. And are blocked to prevent looping frames. So this is how, or this is the key to avoid loop. So if there's a loop like C to D to B to A in a ring, then the redundant ports become alternate or backup and are blocked to prevent looping frames, and this is done by their OS. So to summarize in your phrasing, so you mean all of the that will be put into blocking state. Yes, all non-winning redundant ports such as alternate or backup are placed in blocking state until needed. So you mean the designated port is the best path from switch B's port from root to that segment? Exactly. The designated port is the one that can best deliver frames from the root toward that LAN segment, or from the root B designated port towards the LAN root of that LAN C segment. So backup port is a backup to a designated port. The reason why we said LAN segment is because, remember, a bridge could also be a LAN, right? So it could be interconnected ports. So backup port is a backup to designated port, while alternate is backup to the root. So correct. Alternate port equals to backup to root path. Backup port, backup to a designated port on the same bridge and segment. Topology change. The next important job of STP is to handle topology changes. Although we conceivably use the basic database aging mechanism described earlier to adapt to changing topologies, this is a poor approach because the aging timer can take a long time, 5 minutes, to delete incorrect entries. Instead, STP incorporates a way to detect topology changes and inform the network about them quickly. So STP, instead of waiting for 5 minutes, incorporates a way to detect topology changes and inform the network about them quickly. In STP, a topology changes occurs when a port has entered the blocking or forwarding states. So in STP, it will trigger this, or the OS has an if-else statement that is programmed to detect a blocking from blocking to a forwarding states. What a bridge detect when a bridge detects a connectivity change, like a link goes down, the bridge notifies its parent bridges on the tree. So this is how it notifies it in action. It notifies its parent rather than its child. The reason is you need to be closer to the root bridge so that root bridge can now notify others using the TC bit. So you notify the parent using the TCP and the TCN rather, and you notify from parent or the root bridge to its downstream or to its child using the TC bit. When a bridge detects a connectivity change, a link goes down, the bridge notifies its parent bridges on the tree to the root by sending a topology change notification TCN BPDU out of its root port. So the bridges on the tree, the bridge notifies its parent bridges. That's the keyword, parent bridges on the tree to the root, towards the root. Because for example, you have C, it will notify B, and then it will goes on until root A by sending topology change notification TCN. BPDUs out of its root port. The next bridge on the tree to the root acknowledges the TCN BPDUs to the notifying bridge and also forward them on toward the root. So the bridge or the OS has a code, has the same code, but it triggers a different function which does two things. It acknowledges that it received and also forward it to its parent bridge. Once informed of the topology change, the root bridge sets the TC bit field in subsequent periodic configuration messages. So it will send it in hello time of 2 seconds, the new configuration of BPDU packet. Now such messages are relayed by every bridge in the network and are received by ports in either blocking or forwarding states. So remember, the blocking states are still listened to this root bridge 2 seconds BPDU frames. The setting of this bit field allows bridges to reduce their aging time to that of the forward delay timer on the order of seconds instead of the 5 minutes normally recommended for the aging time. So this bit will then inform those downframe bridges their aging timer to that of the forward delay timer instead of the 5 minutes. That's why it's fast. This allows database entries that may now be incorrect to be purged and relearned more quickly. So this bit, kind of like an if else trigger on the bottom bridge later, will allow them or their database in memory the entries that may be incorrect to purge and relearn more quickly. Yet it also allows stations that are actively communicating to not have their entries deleted erroneously. So at the same time, if those paths are communicating, they don't. This code doesn't delete their entries erroneously. So big picture, why topology change message exists. When something changes, like a cable is pulled, a Wi-Fi link drops, or a port unblocks after recovery, STP must flash state forwarding table entries fast, or else packets will keep getting sent to the wrong port to a dead link. So because of that, if it fails, it will still send, for example, a letter C to B even though that designated port connected to root port of C is already dead. If you waited for the normal Mac aging timer, default 300 seconds, you'd, uh, you'd have black holes or loops for minutes. So if you wait for 5 minutes with that broken link, it could take a lot or long time. So STP speed this up by using topology change notification messages. Step by step, what happens when a link changes? Let's use a real looking chain. Host 1 to bridge C to bridge B to root bridge A. Say C's link to host 1 fails. Bridge C detects link change. The Linux kernel bridge code module br_stp.c sees a port state change. So this C or this exact C has some way, such as br_stp.c code will see a port state change, such as from br_state_forwarding to br_state_down or br_state_blocking. So that's the state of blocking and forwarding I mentioned earlier. At that moment, the bridge marks a topology change and sends a TCN BPDU upstream out its root port, the port that leads toward A. So since it has a copy of a root port, it is allowed or it is able to send a TCN upstream. This TCN BPDU just says something in my downstream topology change. Please flash max. It doesn't list which max or which port, just a change happened. So it doesn't say particularly what MAC address that needs to change. It just tell it that something or the TC bit needs to be calibrated upstream. Now parent bridge B receives the TCN. Bridge B receives the topology change notification BPDU on its designated port from C. It sends back a TCN acknowledgement to C, forward its own TCN BPDU upstream toward A, the root bridge. Each bridge along the path does this relay. Root bridge A receives TCN. Now the root bridge A receives the message and says, got it, topology change somewhere below me. Kinda like the heap stock. It just knows that all of the downstream tree or node is less or greater than it. It doesn't flood another special packet. Instead, it sets a flag inside its regular configuration BPDUs, the topology change bit. So that's what the TCP bit meant we mentioned earlier. From now on, it also the TC bit in the BPDU frame we discussed in the last video. From now on, for the next hello time times max h plus forward delay seconds, every BPDU A sense include TC equals to 1. So this for the next hello time times max age plus forward delay seconds. So these are the seconds. Every BPDU A sense include TC equals to 1. So this is how you compute. These are the formula, mathematical formula. 2 times like 20 plus forward delay 15, right? 20 plus 15. Every BPDUA will now include TC equals to 1 since it just received that, so that it receive all the corresponding, like for example it has a connection from E or F downstream, it has a time to receive those as well. That's why it has this formula. Now downstream bridge receive the TC plug. When B and then C receive configuration BPDUs with the TC bit set, they shorten their Mach aging timers from 300 seconds to 15 seconds, or forward delay equals to 15 seconds. So again, when B and then C receive configuration BPDUs with the TC bit set, they shorten their Mach aging timers. So when B, this is how you turn the 300 seconds to 15 seconds, or forward delay goes to 15 seconds, because they receive, or their OS are coded in which if it receive the TC bit set, it will shorten their Mach aging timers. And aside from that, it is also coded to flash all dynamic Mach entries except on the port the BPDU came from, which is the root port that connected to the designated port of the bridge. That means all the host port mappings like Mach of host 1 is on port 2 are discarded. So that is the what is in their Mach table entry, such as the host 1 on port 2 connected to C. So those are discarded. Now new traffic will cause refresh learning on the correct ports immediately. That's why even those host 1 connected to C failed, after some time and after some BPDU, what you call that, BPDU configuration, in its regular configuration BPDUs, which is included in hello timer, right? Hello time, which is 2 seconds. So this is the magic that keep things consistent across the whole tree. Relating it to earlier STP logic. Earlier you learned each bridge know its root port, designated ports, and maybe block ports. These states change during convergence. For instance, when a link fails, some block port may become forwarding. So this is how block ports, or usually that block port or the alternate port, become then the new root port. Let's say the C port 2 connected to the host 1 port 2 connected to the C failed, and you have an alternate port, let's say from host 2, that has the shortest path. Those block port now will now become forwarding state. So this state change during convergence. For instance, when a link fails, some block port may become forwarding. When that happens, the same mechanism, TCN to root to TCB flood, When that happens, the same mechanism, TCN to root to TCB bit flood, so TCN to root upstream to TCB flood downstream triggers a rapid relearn of max. So bridges don't keep forwarding frames along stale paths. So in that way, in that code of that operating system, in that structure, it is able to relearn of max. So bridge don't keep forwarding frames along stale paths. So avoid keeping or sending packets because all of the frame in the network knows that those port 2 from host 1 failed, so it stopped sending that. It was able to flash that MAC entries already. So the upstream notification TCN moves toward the root. The downstream signal TCB flows from root toward leaves. Together they synchronize the new topology and flash all forwarding info. So this is the network topology change we're talking about. They're able to synchronize the new topology and flash all forwarding info because of that amazing algorithm, which is the STP. So that's the distributed algorithm we're talking about in the previous video. In the Linux kernel, bridge or STP code, inside the Linux bridge module, the logic in net slash bridge slash br stp.c and br fdb.c, each br port struct keeps state, timers, and flags. So in net slash bridge slash stp and the fdb.c, each br or port structure keep its states, timers, and plugs. This is how it kept that state and then the timer and then the flag we discussed in the previous frame structure. When a port's state change, like br underscore state set underscore state port, br underscore state underscore blocking, the kernel calls br underscore log underscore state underscore change. So that's the function it calls. So when a port state change, that's like br underscore set underscore state with the parameter port comma br underscore state underscore blocking, which means that port becomes blocked from forwarding, the kernel will call the br underscore log underscore state underscore change function, which will trigger br underscore topology underscore change underscore detection. It will send TCN BPDU upstream. Now the bridge work queue scheduler BPDU transmission every hello interval 2 seconds by default. So because the bridge work queue schedules BPDU configuration, habitual configuration for BPDU, it was able to send TCB downstream and it was able to flash the MAC address of other bridges. This is all inside kernel space. User space like TCP or IP stack IP layer doesn't run it directly. So it's all in the kernel space. It doesn't work with the TCP IP. So the IP is subtracted from it. Now how it connects to TCP or IP? From the TCP or IP stacks view layer 3, nothing explicit about STP or BPDU is visible. It's all layer 2 logic. What does happen is that some interfaces suddenly flash their neighbor entries, like our table updates, missing packets for a few seconds. This is how the delay comes in. TCP connection may briefly pause or retransmit due to missing ACKs while STP reconverges. So if TCP application recognizes that it doesn't acknowledge, therefore it will trigger a retransmission. In Linux, the bridge driver is below IP in net device layer. So when a port goes blocking, packets to that port are silently dropped. IP doesn't know why, it just sees the link as working but frames disappear for a second. Once convergence finishes and MACs are relearned, normal TCP traffic resumes. So once all the bridges relearn the new MAC, normal TCP traffic resume because it will be able to retransmit the packet. So real world example, imagine a small labs, root bridge A to root bridge B and server 1 and bridge B connected to server 1 and bridge C connected to host 1. Case C's link to host 1 fails. First, C detects the port link. Down, it sends TCN BPDU to B. B acknowledges and forwards to A. A starts setting TC equals to 1 in its config BPDUs. B and C receive them. Flash MAC tables when host 1 reconnects, maybe on another switch port, such as, for example, earlier we are in port 2, maybe now in port 3. Its MAC is quickly relearned, or the MAC of that port. End result, recovery within seconds, not minutes. So analogy, think of it like a fire alarm chain. When one room detects fire, topology change, it triggers the building alarm panel, root bridge, which then sends signal back down to everyone to reset and update, flash old routers. So example in the real Linux world, in Linux, the bridge function disables STP by default on the assumption that topologies are relatively simple in most cases, where a regular computer is being used as a bridge. To enable STP on the example bridge we are using so far, we can do the following. So usually this STP is not configured, it is usually the normal bridge. So to enable that, we will need to input this command, brctl stp br0 on. So this is what we see, bridge ID, designated port, etc. Here we can see the STP set up for a simple bridge network. The bridge device BR0 holds information for the bridge as a whole. So this BR0 has the ETH0 and ETH1. This includes the bridge ID 8000.007E914A9C1. So these are the designated port of ETH0 and the designated root of ETH1. And the designated bridge of both, and the bridge ID of BR0 and the designated root, derived from the smallest MAC address on the PC-based bridge, port 1 of figure 3.11. So these are derived, again, we have a priority on MAC address from the smallest MAC address on this PC-based bridge, because remember, the root ID will become the lowest cost, or the lowest cost and the lowest MAC if it has the same priority. The major configuration parameters, hello time, topology, change timer, etc. are given in seconds. So forward delay timer 00, TCN timer 0, bridge forward delay 14.99, bridge hello time 1.99, max age 19.99, etc. The flags values indicate a recent topology change, which is expected given the fact that the network was recently connected. So here's the topology change timer is actually 3.37 if the it is just recently connected or turned on. So these are the first election. The rest of the output describe per port information for ETH0 bridge port 1 and ETH1 bridge port 2. ETH0 and ETH1, so bridge port 1 and bridge port 2. Note that the path cost for ETH0 is 100, or about 10 times greater than the cost of ETH1. This is consistent with the observation of that ETH0 is 10 millibytes per second Ethernet network, and ETH1 is a full duplex 100 millibytes per second network. So because it has this 100 millibytes, it is its path cost, it is faster basically. So the network will choose this as its default from its downstream bridges. Now we can use Wireshark to look at BPDU in figure 3.6. We see the contents of a 52-byte BPDU. The length of a 52 bytes less than the Ethernet minimum of 64 bytes because the Linux capture facility remove the padding is derived from the length or type field of the Ethernet header by adding 14. That is why we have this 52 bytes. In this case, giving the length of 52. The destination address is group address 0180 C2000, which is the default for IEEE. So you can see frame 1 51 bits, 52 bytes on wire or 416 bits. IEEE 802.3 Ethernet. The destination address is group address as we expected. The payload length is 38 bytes, which is this. The value contained in the length field 38, and source, this is the source MAC of this port, showing a BPDU. So the Ethernet destination is a group address for bridges. So this is how we see the BPDU in action in Wireshark. Now the snap or LLC field contains the constant 0x424243. So where is that? Here the 42, the spanning tree, this snap, and the SS up spanning tree BPDU 0x42, 0x42, and 43, and the encapsulated frame is a spanning tree version 0 frame. So here spanning tree protocol version 0, and protocol identifier spanning tree protocol, BPDU type configuration, BPDU flags 0x00, root identifier 32768/0/, this is the MAC source address. The rest of the protocol fields indicate that the station 0007E914A9C1 believe it is the root of the spanning tree using priority 32768. So here's the root identifier. It means that the rest of the root believes this is the MAC address of the root bridge. Root bridge priority extension 0, root bridge system ID, root path cost equals to 0. When you see this root identifier and root path cost, it means you found the root bridge. Bridge identifier 32768 extension message 0 max h hello time 2 forward delay 15. And the BPDU has been sent from port 2 with priority 0x80. It also indicates maximum age of 20, a hello time of 2 seconds, and a forwarding delay of 15 seconds. The two pieces you're seeing, we've shown two things: Wireshark BPDU capture 3.16, a live STP configuration BPDU sent over Ethernet by Linux Bridge BR0. So it's actually a live current inspection of the packet being sent of this port. So remember, the frames being sent is being divided through IP. So we just chop one of that to examine what it actually shows. BRCTL show STP BR0 output. So that's the internal kernel data representing the bridge STP state, timers, IDs, costs, etc. There are two views of the same mechanism. BRCTL shows STP, shows what bridge kernel module knows and believes. So this command will show what the bridge kernel module or the Linux knows and believes to be the information on that frame. The BPDU in Wireshark shows what the bridge actually transmit on the wire every hello underscore time seconds, default 2 seconds. So these are the frame being sent every 2 seconds. So one of the frame. The previous, this is that the every 2 seconds, while these are the information believed by the Linux. So let's go line by line. Bridge ID. So in BRCTL show STP, bridge ID 000.007E914E9C1. In Wireshark, BPDU bridge identifier equals to 32768/0x8000 plus MAC 0007 E914 A9C1. Designated port, designated route 8000.0007 E914 E9C1. In Wireshark, BPDU route identifier equals 32768/0x8000 plus MAC 0007 E914 A9C1. Hello time 1.99. BPDU field, hello time equals to 2 seconds. Max age 19.99. BPDU field, max age equals to 20 seconds. Forward delay 14.99. BPDU field, forward delay equals to 15 seconds. Root path cost, root port 0/cost 0. BPDU field, root path cost equals to 0. Flags, topology change in BRCTL show STP topology underscore change underscore detected, which is the 3 point something. In Wireshark, BPDU flags TC equals to 0 may later become TC equals to 1 when TCN occurs. So as you can see here, we have TC equals to 0. So currently we have TC equals to 0 here. So cost equals to 0, port 0x800, root, time, number, source, destination, protocol, These fields are one-to-one translations between the internal bridge kernel structure struct net underscore bridge underscore STP and the bytes that the kernel encodes in the outgoing BPDU packet. What happens internally in the Linux kernel when you enable STP, BRCTL STP BR0 on, Linux loads the spanning tree state machine inside net underscore bridge, inside net slash bridge slash br underscore stp.c. Each interface enslaved to BR0, like ETH0, ETH1, becomes a bridge port with its own BR underscore port struct. Each port state machine cycles through disabled to listening to learning to forwarding. Every hello underscore time seconds equal 2 seconds by default. The kernel builds a BPDU frame in memory. So this is how the frame are being created. It is being created by the logic of the Linux in its memory. It fills in the fields using current BR0 values, root ID from elected root, bridge ID, path cost, port ID, timers. It sends that frame to destination 01 ATC2000000, a reserved Ethernet multicast address for bridges. So that's exactly the frame you see in Wireshark. How it fits in BPDU exchange logic. Because the Linux bridge is currently the root bridge, designated root equals to bridge ID. It sends configuration BPDU downstream on all forwarding ports. It does not have a root port since it's the root itself. Include its own bridge ID as both root ID and the bridge ID. Each downstream bridge, if there were one, would receive the BPDU. Compare IDs, realize this bridge has a lower ID and adopt it as its root bridge. How Wireshark shows the protocol. The Wireshark breakdown corresponds exactly to the IEEE 802.1d fields. BPDU field, protocol ID equals to 0x0000, meaning STP BPDU. Linux kernel source BPDU to protocol underscore ID. BPDU field version equals to 0, meaning 802.1d STP. Linux kernel source BPDU to protocol underscore version. Type equals to 0, configuration BPDU. Linux kernel source BPDU to BPDU underscore type. Flags equals to 0, no topology change currently. BPDU to flags. Root ID, lowest bridge in topology. BR2 designated underscore root. Root path cost, cumulative cost, BR2 root underscore path underscore cost. Bridge ID, sender's ID, BR2 bridge underscore ID. Port ID, local port identifier, BR underscore port to port underscore ID. Message age, 0, root starts count, incremented downstream. Max age /hello /FWD delay, timing constants from bridge timers. So what you see in Wireshark isn't just a capture, it's a serialized copy of the internal STP structure inside BR0, sent by the Linux kernel every 2 seconds. In TCP or IP stack terms, here's how this interacts with the rest of the system. Layer 2, the BPDU is a special Ethernet frame, Ether type 0x0000/LLC 0x424203. Layer 3 IP, it does not see this at all. These frames never get passed up to IP or TCP. User space, if you run Wireshark or TCP dump -I BR0-N STP, it listens in promiscuous mode and decodes it at layer 2. Bridge kernel module, it handles the generation, receipt, and interpretation of BPDUs entirely within kernel space. It updates port states, flashes MAC tables, and run timers without any user space daemon, unlike Cisco switch, which run STP in firmware. Real-life interpretation, this example from your screenshot is the simplest possible case. A Linux PC acting as a small switch, bridge, BR0 with ETH0 and ETH1, no other bridges, it's automatically the root. It sends out configuration BPDUs every 2 seconds to maintain control. You can see these same packets in Wireshark because Linux bridge kernel is actively talking STP on your behalf. If another Linux box or switch joined, both would exchange BPDUs, and the one with the lower bridge ID, priority plus MAC, would become the new root. Then your current 100:07:E9:14:A9:C1 would stop sending I am root messages and instead forward the superior BPDU it receives. TLDR summary, kernel bridge module, BRCT action computes STP state, build BPDU, sends every hello time. Layer, BRCTL show STP, it reads kernel internal STP variables. Wireshark BPDU, the actual on-war STP frame built from those variables. Ethernet multicast 01ATC2000000 ensures all other bridges see it, but host ignore it. IP/TCP layers, completely unaware this happens below them.